Alrighty, let's finish up this packet. And I forgot my Chromebook, so I'm having to use my camera. So please be patient with me. All right, I can't remember if we did number 15 or not, so we're going to go ahead and look at that. So this is methylamine, which was CH3NH2. That was one of the 3 weak bases that were listed in our notes that are pretty common to see. So we're going to do our reaction. Add water. Since it's a base, it's going to accept a hydrogen. This should have been a 2. CH3NH3 plus OH minus. So my initial concentration would be 1 molar. I'm not worried about the water. This would be 0 and 0. My change would be minus X plus X plus X. And so in equilibrium, I would have 1 minus X, X, and X. So we probably didn't have to really do a rice chart on this because it kind of just follows the typical way that we've seen. So we're going to end up with 4.38 times 10 to the negative 4th. So that's going to be my KB. And I'm going to kind of do a little wavy equal sign that shows it's about. That would be a good thing maybe to do on your AP chemistry to show that you're dropping your X. And so this, by showing that, that kind of gives the graders a sense that you know what you're doing. So I end up with my X squared over 1. And so when I solve for that, I get X is equal to 0.021. And that is going to be equal to my hydroxide concentration, because notice that we have a hydroxide, it's the base. And you need to put this, you need to put that you know what that X represents, because we're trying to get to pH. So you can't just all of a sudden show up with the pH number at the end and expect to get any points. You've done the hard work. Now these simple things are where you want to make sure that you do your work and show your things. And so you'll get those credits. So the first thing I'm going to have to do is get my POH. So I do negative log of 0.021. And that gives me a POH of 1.68 with 2 sig figs, because that's how many sig figs my concentration had. And then to get my pH, because that really is what's being asked, I'm going to take 14, minus 1.68, and then I would end up getting 12.32, and that would finally give me my answer that I was looking for. Once again, you can't go from solving for your X and all of a sudden put down a number for pH, and you're not going to get credit on my test. You're not going to get credit on the AP test. You need to show how you get there. This is the hard part. This is the easy part. So don't lose points here on either test, you know, when you've done the hard part. All right, so now we're going to look at determining the pH of salt. And if you remember from chemistry, we did neutralization reactions where a salt was formed. And a salt doesn't have to just be sodium chloride. A salt is an ionic compound where the cation, the positive ion, is from the base. Lift up from base, and anion, it's negative, is from the acid. So ionic compound, cation positive from the base, and the negative ion is from the acid. So think of sodium chloride. Sodium came from sodium hydroxide if we were doing a neutralization reaction. and that's a strong base, and the Cl came from hydrochloric acid if we were doing a neutralization reaction. Sometimes I struggle a little bit with this part of it, maybe explaining it more than actually do the problems. And just kind of remember, we're going to be using the Bronsted-Lowry definition. So that means that an acid is going to donate an H plus and a base will accept that H plus. All right, so the easy ones and the ones that we did just in Chem 1 are neutralization reactions. And those are when a salt is formed from the cation of a strong base and the anion from a strong acid. And it forms a neutral solution, so pH equal to about 7. And we call these neutralization reactions. Special type of double replacement reaction. So an example of that would be kind of like I've talked about, sodium hydroxide mixed with hydrochloric acid. It's going to end up giving me sodium chloride, which would exist as ions in an aqueous solution, plus H2O. But not in excess of the hydronium ion, not in excess of the hydroxide ion. So it would end up being neutral. So if I wanted to actually collect that sodium chloride to make table salt, I'd have to get that water off, and then they would go out of solution. So they would go back and form a solid. All right, so to get an acidic salt, the salt is formed from the cation of a weak base and the anion from a strong acid, and that gives us an acidic solution when it's dissolved in water. So an example of that would be NH4Cl. Remember, a strong acid or a strong base, our list of strong acids, our list of strong bases, those ionize about 100% in water. Weak acids and weak bases do not ionize up to 100%. So if we think of NH4Cl, if that's my salt, it would have come from mixing hydrochloric acid, which is a strong acid, and then I would have had ammonia, which is a weak base. So that's the things that they in a water solution, in an aqueous solution. So that's how I would have gotten that salt. The cation, the positive ion, hydrolyzes the water molecule, and it means the positive ion of the salt hydrolyzes the water molecule to produce hydronium ions, and thus it ends up being acidic. The anion, in this case, the negative ion, is just a spectator ion. It's just going to remain as an ion. It would cancel out if we were doing it ionic. Hydrolyzes the water just means it breaks it apart. So here, because I had a weak base, its conjugate acid would be stronger as an acid than the base, the conjugate base that was formed from my strong acid. So the conjugate acid would be a stronger acid than the conjugate base that's formed. And if something is a stronger acid, that means it's more likely to donate a hydrogen. If it's a strong base, then that means it's more likely to accept a hydrogen. So in this case, a conjugate acid that was formed from my ammonia, from my weak base, is a stronger acid than the conjugate base form. So really I become interested in what's happening with my cation. So my cation, it hydrolyzes water, breaks it apart. Since it is an acid in this case, actually a conjugate acid from original reaction, if you want to kind of think about that. So it's going to donate the hydrogen, and I'm going to go back to being a weak base, and then we end up with this hydronium, so we end up with a strong acid. So this is meaning that our pH should be less than 7. All right, now if we think of our basic salt, meaning it's going to have a pH greater than 7 if it's a basic salt. Salts are formed from the cations of a strong base and from the anion of a weak acid. And it forms a basic solution when dissolved in water. So once again, because my strong base is, since my base is strong, it's going to be almost dissolved or almost ionized. My weak acid will not be nearly as ionized, and that's what's going to contribute in the end to the pH. So if I have NaC2H3O2, that originally came from the Na, sodium hydroxide, and the C2, that H3O2, the anion would have been acetic acid. So there's my strong base, my weak acid. So in this case, the anion, the negative ion, is going to be the one that's going to hydrolyze the water, and it's going to produce hydroxide ions and thus a basic solution. In this case, the cation is just the spectator ion in this one. So since I started with a strong base, the conjugate acid in this reaction is weaker than the conjugate base that is formed. Because the conjugate base came from a weak acid. Remember, if we have a weak acid, it's going to be a stronger base and vice versa. That doesn't mean it goes into the list of really strong bases like sodium hydroxide, but that means it's going to be a stronger base, so more likely to accept a hydrogen than the acid was to donate a hydrogen. Okay, so an example of that. So now we said that in this case, the anion is going to hydrolyze. So now I'll become interested in the anion or the negative part. So that would be my acetate ion. And remember, it is a base. I'm going to say it's a conjugate base because that's how it was formed. Now, if I mix it with water, it's acting as a base, so it's going to accept the hydrogen, and then I end up with hydroxide. So that's why I'm getting my base right there. All right, so let's look at some questions that kind of pertain to that. And actually, I think I rewrote that equation there at the top that you probably didn't need to, but anyway. All right, so let's see if I can get this. Make a little adjustment, sorry, y'all. I'm not used to doing it this way anymore. All right, so let's look what we got here. So when determining the exact pH of salt solutions, we can use the Ka of a weak acid formed to find the Kb of the salt, or if we know the Kb of the weak base that's formed, we can use Ka. And we do that by this relationship. Ka times Kb is equal to Kw. And Kw we did earlier was 1.0 times 10 to the negative 14 at 25 degrees Celsius. And you just, unless stated otherwise, you just kind of assume that that's what condition. So remember, I would be using a Ka because that's equilibrium for an acid. So I would have to start with an acid, and then it would have to donate H plus. And if it was Kb, I would have to start with the base and accept H plus. And the reason I put that is sometimes it's a little bit confusing which one to use for which reaction. And we're going to do some problems in a little bit, and that'll make a little bit more sense. Excuse me. All right, so the general order of pH is your strong base is going to have your highest pH. Then after that, weak bases. Then basic salt. So a basic salt is when you have a strong base with weak acid. That's your combination. Then neutral salt is whenever you have strong, acidic salt. So now we're kind of going right here. We're at like 7. And so now we're spilling over to the more acidic side. So acidic side is going to be when I have a weak base with a strong acid. And then a weak acid would be any of our acids that aren't listed on our strong acid list. And then our strong acids would be those that we talk about, our strongest that were listed earlier. All right, so let's just look at an example of those. If you want to pause it and try and then come back to the explanation, you can do that. So we're asked to rank a mixture of compounds by the pH, label each as shown above, and then arrange them. So when I come down, then I read my question. It says arrange the following 0.1 molar solutions in order of decreasing pH. So that means I need to start with highest pH first, which should be a strong base. So if I come and I start labeling these, I see my strong base right there, sodium hydroxide. I also down here see a strong acid. I see another acid, phosphoric acid. I know it's not a strong acid, it's a weak acid. Also right here, this CH3NH2, this would be a weak base. That's one of the ones that was listed along with ammonia. All right, so I got my strong. So now I got to start dealing with my salts. This salt right here would have come from potassium hydroxide. That would have been a strong base, and hydrochloric acid, a strong acid. So this would be a neutral salt. NaCN, that would have come from sodium hydroxide. So a strong base with HCN, cyanic acid, which is a weak acid. So this is a basic salt. And then my NH4NO3, that would have become from NH3, which is ammonia, weak base. And then that would have come from nitric acid, which is one of my strong acids. So this is a strong salt, or not strong salt, acidic salt. So now I can just start putting them in order. Strong base would be first. Then weak base would be second, CH3NH2. Then basic salt would be next, NaCN. Then neutral salt, KCl. And now I'm going to start coming down on my acidic side. So start with my acidic salt, NH4NO3, and then my weak acid, and finally my strong acid. So that would be going from highest to lowest pH. All right, let's look at a couple of problems with this. So calculate the pH of a 0.3 molar solution of sodium fluoride. So when I think of that, that would have come from sodium hydroxide, which is a strong base, and hydrofluoric acid, which is a weak acid. We talked about that earlier. Usually the halogens form strong acids, but because that fluoride ion is so small, the hydrogen is able to get really close to it. And even though it's very electronegative, that hydrogen is still held on to very tightly. So strong base, weak acid tells me that my pH should be basic. So it should be greater than 7. So if you work on your problem and you get a number less than that, you need to go back and regroup. I had the Ka, okay? So if I had the Ka, that's going to go along with this. So HF is going to form H plus F minus. So this was my acid. This was my conjugate base. So this is what I become interested in. because since it comes from a weak acid, it's not going to want to stay 100% ionized. It would like to get with some water and reverse this reaction and go back to being the HF. So if you're going to form a basic salt, then when you look at your reaction, what you end up becoming interested in is your Kb. So here, this is a Ka. So that's my 7.2 times 10 to the negative fourth. Like I said earlier on this page, I use a Ka when I start with an acid and it donates the hydrogen. So now I take my conjugate base and it's going to combine with water. And it's going to form HF plus OH minus. And that's why I'm going to end up having a basic pH on this. So this is the one that I'm interested in trying to get my information from. So this needs a Kb because I'm starting with the base. In this case, the F minus, it accepts a hydrogen. So I need a Kb, which I don't know. But I know now how I can relate them. Kw is equal to Ka times Kb. So if I kind of rearrange that, I get Kb is equal to Kw divided by Ka. And then I'm just going to plug in my numbers. We know Kw is 1 times 10 to the negative 14. And then my Ka was given to me, 7.2 times 10 to the negative 4. So I end up getting a Kb equal to 1.39 times 10 to the negative 11. All right, now I have that information. It's a very small number. So when I start working with this, I should be able to drop my X. It's going to be a very small number. All right, so this would be my reaction, my initial. It says I have 0.3 molar sodium fluoride that would completely ionize. So that means this starts out at 0.0 molar. We're not worried about the water. To begin with, this is nothing and this is nothing. The change is going to be minus X plus X plus X. And so my equilibrium is going to be 0.30 minus X, X, and X. So that's a Kb. So I'm going to take 1.39 times 10 to the negative 11 is going to be equal to X squared divided by 0.3. And once again, I'm kind of going to do those little abouts so they show that I dropped my X. And when I solve for that, I get X is equal to 2.0 times 10 to the negative 6. Now I used a Kb, so that means I produced a base. I produced a hydroxide. So this is going to be equal to my hydroxide concentration. Up in the problem, I'm trying to find pH. So I'm not finished yet. So my first thing that I would have to do is I would have to find my pOH, which is negative log of my hydroxide concentration. Once again, you have to write these steps to get credit. If you just go from this and all of a sudden you have a pH, you're not getting credit for that on the AP test or on my test. So you got to take these steps. So this gives me a pOH of 5.70. But I wanted pH, so I'm going to say pH is equal to 14 minus 5.70. So I end up with a pH equal to 8.30. And that would be my final answer. This is considered 2 sig figs. I look at my concentration, it had 2 sig figs. So I want my pH to have 2 sig figs. That means places behind the decimal. All righty, let's look at our next problem at the top. All right. All right, calculate the pH of ammonium chloride in the KB. So the B, so that's for a base of ammonia, because ammonia is the base, and they give you a value. So if I think of NH4HCl, if that's my salt, it would have come from NH3, and I think I wrote that wrong, NH4, I got ahead of myself. NH4, this should just been Cl, sorry, and hydrochloric acid. So this is weak base, strong acid, strong wind. So my pH should be less than 7. And really at this point, you're almost not really interested in anything about the strong anymore, because the strong is going to stay ionized. The chloride ion is not going to hydrolyze the water because it stays about 100% ionized. So really, just like the other one, I become interested in my weak, what's going on with my weak. So if I think of my weak as a base, that's going to be my ammonia. And that's going to give me my NH4 plus, my cation, plus my OH minus. All right, so when we said when we have a strong acid, the cation hydrolyzes or breaks the water down or adds to the water to give me NH3 plus H3O plus. And that's why I end up having a pH less than 7. So this is my Ka that was given, I'm sorry, Kb. Ammonia is a base. This was my Kb that is was given to me. I took the conjugate acid of that problem, and that became the reactant for my next one. So that means I need a Ka right here. So once again, I'm going to do that same little trick using that same formula. Let's say Ka is equal to Kw divided by Kb. So Ka is going to be equal to 1 times 10 to the negative 14 divided by 1.8 times 10 to the negative 5. And that gives me 5.56 times 10 to the negative 10. Once again, a really small Ka, so I should be able to not worry about my X on this one either, which is kind of the goal most of the time. All righty. So now I'm just going to start with my problem. And really, since I have my Ka, I'm not going to have to do a rice table since we're going to ignore the X. So I end up with my Ka 5.56 times 10 to the negative 10th is going to be equal to X squared divided by 1.0. So I end up with X is equal to 2.36 times 10 to the negative 5th. And that is my hydronium concentration. So this is equal to my H plus concentration. Remember, hydronium and H plus, same thing. So that means if I want to find my pH, negative log of 2.36 times 10 to the negative 5th, and my pH would be equal to 4.63. Once again, I need to be sure and put what I know my X is equal to, and I need to be sure and put how I'm taking that X value and getting it to a pH or a POH. 2 sig figs, 2 sig figs in the concentration. All right. And then at the end, just a couple of things. Metallic oxide, so that's the metal and the oxide. Those are ionic compounds combined with water to give you a metal hydroxide. So that means they're going to give you a basic solution. We did both of these in types of synthesis reactions, both in Chem 1 and also at really the beginning of the year. A non-metal oxide, so that would be a covalent compound like CO2 will combine with water to give you an acid. And it would be a weak acid, and that would give you an acidic solution. Then we have these other things that are kind of strange looking, very complicated looking. Salts that contained a highly charged metal. So example, that would be aluminum with a +3 charge. That's what they mean, highly charged. Produces an acidic solution. So if I have aluminum chloride and I combine it with water, I'm going to end up getting what's called a hydrate. Sometimes instead of written like this, you'll see them written like, how many does that say? 6H2O. You'll see it written like that. This one had a charge +3. But it's going to then, that metal hydrate, whenever it's put in with water, it's going to lose one of the hydrogen because they're not going to be held on to very tightly. And then I'm going to get my acidic solution. So really, you don't have to do much work in this. If you saw something that looked really weird, then you might be asked what kind of solution it would form, and it would form a acidic solution. And it has 6 waters. One of the waters loses a hydrogen, not all of them. And that's how we end up having the hydronium, the H+, the acidic solution. If you notice, the charge also went down overall to a +2. The higher the charge on the metal ion, the stronger the acidity of the hydrated ion. So that's what we're talking about here. The electrons are pulled away from that OH bond toward the positively charged metal. And so it's easier for that hydrogen to be lost. Because remember, if we're looking at, so there we could say that's a bond in one of the waters. So what they're saying, this aluminum is very charged. So it really attracts the electrons that way and that way, leaving that hydrogen kind of to be hanging out by itself. So it's easy for it to lose that hydrogen to give an acidic solution. You'll see that also with iron chloride, because the iron in that case 3, and then aluminum nitrate would be another time that you might see that. All righty, hopefully that all recorded good, and I'll get that one posted, and we'll see what else I can get done today.